CfA Seminar. Our first speaker today will be Lekshmi Thulasidharan from the University of Wisconsin-Madison. She'll be talking about some work on the accretion, the merger history of the Milky Way.
For introduction. Hi, I'm Lekshmi, and I'm a graduate student at the University of Wisconsin-Madison. So today I will be talking about my most recent work on decoding the merger history of the Milky Way. And these are my close collaborators, without whom this work would not be possible. So let me start by talking about why understanding the merger history of the Milky Way is important.
All right, maybe we'll not use it. We might just have to press the button. We'll go back to the beginning.
So is it possible to then highlight?
We're going to stick.
You can use
the laser pointer.
You still use the laser pointer. Yeah.
Oh yeah. Okay.
Back then.
Yeah, I've just got to do that, so I need to go back.
Yeah.
Sorry about that.
Okay, so let me start by talking about why understanding the merger history of the Milky Way is important.
No, it's not.
It's not that. It's something.
No, that's strange.
You could just try closing it and then redoing that presenter. Yeah.
Oh,
And then try.
no. I don't know why.
This is crazy.
Has anyone seen this before?
So what you might want to do is just try clicking this. Click this.
No, it's going. I don't know.
Okay.
It's just something.
I think that maybe it's the use timing. Do not use timing. Let's play narration. Boom.
Oh.
Problem solved.
Okay, sorry about that. So let me start by talking about why understanding the merger history of the Milky Way is important. The hierarchical theory of galaxy formation says that galaxies form gradually over time by accretion and mergers of small satellite galaxies. So now with all these data coming in from various sky surveys such as Gaia, Milky Way is like an excellent setting for testing these theories of galaxy formation and evolution. So how do we normally, usually, go about reconstructing the merger history of the Milky Way? So the conventional method for understanding the merger history of the Milky Way is by looking for substructures in the kinematic spaces, such as the energy angular momentum space. And if such substructures also feature different chemical abundances, we infer them as separate instances of accretion. However, a recent work by Morey et al. Cast some doubts about this approach. So in their study, they found that the satellite stars with different metallicities can in fact show up in different regions of the energy angular momentum space. So that means a single accretion event can manifest as different metallicity distributions in different regions of energy angular momentum space. So that means there might be a bias in the conventional approach for piecing together Milky Way's merger history. So there could be a bias towards overestimating the number of past accretion scenarios and underestimating the mass of the progenitor galaxy. So this shows the importance for more robust or at least complementary approaches for distinguishing between various accretion scenarios so that we can reconstruct the merger history of the Milky Way more accurately. So it's been known since the early 90s that the interactions with satellite galaxies can significantly heat up the stars in a galaxy's disk. And this process could alter the structure of the disk of the galaxy, especially in the vertical direction. So here is a series of snapshots from Quinn et al. 1993, where we can see the evolution of the galactic disk over time after it encounters an interaction with the satellite galaxy. So as you can see, over time, the thickness of the disk increases. So the vertical positions of the stars start to inflate over time. So that means if we can trace the vertical thickness of the stars as a function of age of stars, we can potentially identify the number as well as the intensity of these past interactions Milky Way has had with other satellite galaxies. So basically, we can use the vertical thickness of the Milky Way stars as a probe to reconstruct the merger history of the Milky Way. And in order to do that, we take two of the most recent samples from LAMOST as well as SDR12. Both of these are value-added catalogs with stellar ages. A LAMOST catalog consists of red clumps and red giants, whereas the SDR12 catalog consists of metal poor stars in the galaxy. We then select the stars between 8 to 11 kiloparsec in galactocentric distances in order to minimize distance uncertainties. We also limit the stars within 3 kiloparsec above and below the midplane in order to make sure our sample is mostly dominated by the disk stars. And once we have the sample ready, we divide the sample into, we divide the ages into bins, and for each age bin, we calculate the vertical dispersion of position of the stars as a proxy for disk thickness, and we call this diagnostic delta C. So this is the age delta C relation that we found with the sample, with the stars in our sample. So there are some interesting observations we can make here. So there is an overall decrease in the vertical thickness the younger the stars get. In addition to that, there are these features such as there is a jump from a region of higher vertical dispersion to a region of lower vertical dispersion at around 11.13 gigayears. There are also, in addition to that jump, that transition, we can also see some minor bumps in the data at around 5.20 gigayears to around 2 gigayears, and then one of the more, around 0.22 gigayears. We then also checked the kinematics. We divided the ages into bins and then calculated the dispersion in vertical velocities. And interestingly, the kinematics confirms the trend that we see in the age thickness relation in the data. So in order to understand what this means, there are certain features such as a jump from high delta C to low delta C region, as well as these minor bumps in the data. So in order to understand what these features mean in the context of the merger history of the Milky Way, we look at some of the Illustris TNG simulation, Milky Way analogs from Illustris TNG50 simulations for more insights. So here is a Milky Way analog, let's call it model 1, from the Illustris TNG50. So this galaxy has underwent a significant merger in its past, starting from about 10.5 billion years ago, lasting until about starting around 10 billion years ago, lasting until 6.5 billion years ago. So this is the present day snapshot, the age delta C relation of the stars in the present day snapshot of that galaxy. So we can notice two interesting observations. So one is that there is an overall decrease in the vertical thickness as the younger the stars get, so which is expected. In addition to that, there is also this significant deviation right here, which starts around 10.5 billion years, peaks at around 9 billion years, and then transitions, there is a sudden decline until 6.5 billion years, after which it transitions to a region of lower vertical thickness. So this is how a major merger, the signature of a major merger manifests in the age delta C diagram, age delta C relation of the stars. So a significant merger can heat up the pre-existing stars in the disk, leading to the formation of the geometric thick disk. So that would explain this region with higher vertical thickness, higher delta C. And then this transition right here shows the time it takes for the galaxy to settle down to finish the merger and then settle down after the merger. And after that, once the galaxy settles down, the new stars formed will have less vertical thickness, which leads to which is basically what we call here as the geometric thin disk. So that would explain this region of lower vertical thickness. So this is how, this is the signature of a major merger in the age delta C plot. Now how about a flyby? So here is another Milky Way analog model. Let's call it model 2. So from JWST and G50. So this galaxy underwent a significant flyby interaction starting around 3.2 gigayears ago, lasting until about 1.6 gigayears ago. And interestingly, in the age delta C relation, we can see a minor bump in the data in the stars that were born during that interaction time. And the peak of this age delta C bump corresponds to the time of closest approach of the satellite, as we can see from this diagram. So here we plot DSH, which is the distance between the satellite and the host over time. So as you can see, as the satellite approaches closer and closer to the host galaxy, the vertical dispersion of the stars which were born at the time goes up. And once the satellite moves away from the host, the vertical dispersion in the thickness, vertical thickness of the stars which were born at during that time goes down. So this is how a flyby manifests in the age delta C relation. A minor fluctuation in the age delta C profile with the peak corresponding to the time of the closest approach of the satellite. So here are more snapshots from more galaxies from JWST and G50. So how does how does the signature of multiple pericentric passages of the same satellite manifest in the age delta C diagram? So here is another model 3, which underwent where we can see in the age delta C diagram 3 peaks corresponding to the 3 pericentric passages of the satellite. So this trend right here is similar to what we see in this region, in region 1 of the data, in the age delta C relation of the Milky Way stars. So here in region 1, so we divided this plot into 2 regions, region 1 and region 2, where region 1 corresponds to the region of relatively smaller vertical thickness. So here we see similar a similar trend, like 3 peaks. So which could be inferred as the 3 pericentric passages of the Sagittarius dwarf, as evidenced by some of the previous studies, such as like from the star formation history of the Milky Way, from the star formation history of the Sagittarius dwarf, as well as from the phase mixing times interpreted from Gaia phase spiral. In addition to that, there is a recent study by Das et al. Where they also found an increase in the vertical velocity dispersion of the stars which are born around 6 gigayears. So that is also consistent, and they interpreted that as the first pericentric passage of the Sagittarius dwarf. So that is also consistent with what we see here in the data. Now, like, how does multiple major mergers manifest in the age delta C diagram? So, like if a galaxy, so this Milky Way analog model 4, this galaxy has undergone 2 significant major mergers in its evolution. So there is a 1:1 merger around 8.24 gigayears, and then while the galaxy was relaxing from that merger, there was another significant merger, a 1:10 major merger at around 6.83 gigayears. So both of these signatures are visible as 2 jumps, after which it transitioned to a region of lower vertical thickness. We can also see a minor bump there. So that's also a merger, but it's a minor merger, while the galaxy was relaxing from the 1:10 to the 10:1 merger. So interestingly, the amplitude of the peaks reflects the relative merger ratios, where like so the more massive merger corresponds to a larger amplitude in the age delta C diagram compared to the less massive merger. So do we see the same thing in the data? Like, can we see signatures of multiple mergers in the data? So as of now, with the data that we have, we don't see much of we don't see signatures of multiple major mergers. All we see here is a transition from a higher delta C region to a lower delta C region, starting from about 11.13 gigayears, lasting until about 8.5 gigayears. So this time is consistent with the timings derived for the Gaia-Sausage Enceladus major merger from these previous studies. So what we see here is the transition. The transition basically marks, the Plato basically marks the transition from a geometric thick disk to a geometric thin disk, which also marks the time it took for the galaxy to relax from, to settle down after the interaction with the GSE merger. So does that mean we can rule out the possibility of multiple mergers? So in order to understand whether we can rule out the possibility of multiple major mergers in the Milky Way, we look at the impact of age uncertainties on the detection of merger events by introducing similar uncertainties, introducing age uncertainties into the simulations, which reflect the age uncertainties in the data. So in the Milky Way analog model 3, where we saw 3 passages of the satellites, similar to what we observed in the data, we introduced an age uncertainty of about 30%, which reflects the uncertainty in the Lamo sample, which is, Lamo sample is what dominates in the 3 peaks that we saw in the region 1. So we introduced 30% uncertainties, and we can see that even after introducing the 30% age uncertainties, we can still recover the 3 peaks. So for younger stars, age uncertainties is not much of a problem, at least with the current uncertainty estimates. But things get difficult as we look at the merger signatures in the older stars. So this is a Milky Way analog model 1, where we introduced an age uncertainty of about 20%, reflective of the SD-SSDR12 ages, which is what dominates the metal poor disk. So here, like, we can see that introducing an age uncertainty, we can still distinguish the signature, we can still identify it's a major merger, but it gets obscured. The signature gets, the peak gets broadened and the signature gets obscured. So if there are multiple major mergers, these age uncertainties would pose a problem. So because we will not be able to distinguish between two major mergers anymore, because age uncertainties could obscure the signatures of both of them. So that could possibly lead to us identifying a single merger. We could be misinterpreting multiple major merger signature as a single merger signature. So as of now, we cannot rule out the possibility of mergers other than the GSE in the Milky Way, but with improved age estimates, if Milky Way has had multiple mergers before GSE in the past, you should be able to see 2 peaks in the metal poor part of the disk with this simple diagnostic. So I would also like to highlight another work that we are currently doing, where we are looking at the signature of a major merger in the world. So Han et al. Gave a compelling evidence last year that the Milky Way warp is likely caused by a major merger, such as the GSE merger. So building upon that work, we looked at the warp in the galaxy, in the model galaxy, Milky Way analog model 1, and we looked at, we colored the XY plane as a function of average C in order to see the warp signature for the gaseous disk, for the stars which are born after the merger and for the stars which are born before the merger in the present day snapshot. So what we see here is that the stars which are formed after the merger, which is this population here in the delta C diagram, so they follow the gaseous disk. The warp signature, the post-merger stellar warp follows the gaseous warp. Whereas the pre-merger stellar warp, they are misaligned they're misaligned in the azimuthal direction compared to the post-merger stellar disk. So you can also see this very clearly in the Y versus average C diagram, where the post-stellar warp and the pre-merger stellar warp are warped towards different directions. So this would give you an independent, so given we have enough data in the Milky Way, given we have enough data of the stars in the Milky Way, this could potentially give another metric to identify when the major merger happened in the galaxy, provided the warp is formed due to a merger. So this is another independent, this will give you another independent estimate of GSE merger if GSE merger caused the warp. So coming to summarize, like we showed that the age thickness trend gives a blueprint of the major interactions the Milky Way has had in the past. So the data shows evidence of a major merger, which is likely the GSE merger, and 3 pericentric passages of a satellite, likely Sagittarius dwarf. We cannot currently exclude the possibility of other proposed major mergers, such as the Kraken merger proposed by Krushen et al. 2018. We also marked the transition from the geometric thick disk to the geometric thin disk, which also tells us the time it took for the galaxy to relax after the major merger. And like with the warp, like if it is formed due to an impact of a major merger, shows an azimuthal misalignment between the pre-merger and post-merger stellar population that could give you an independent estimate of when a merger happened, provided the warp is due to a major merger. Thank you.
Thank you. Are there any questions?
Sorry, I arrived late, you may have mentioned this, but what about globular cluster mergers? There, one, I think, that has been talked about for years, I think it's Palomar 29 or something, that name. But this is a very interesting question of, with dwarfs or dwarf galaxies, presumably don't have appreciable globular cluster components, but I guess the question I'm asking is, can you distinguish between something like Sagittarius, dwarf, and globular clusters? Because there's at least one, and I think there are several more globulars that have got, you know, tails of stars being disrupted, so they're clearly merger events. So it would be interesting to see if those show up with this kind of analysis.
Yeah, we haven't checked it, but that would be an interesting thing to look at in the simulations with JWST and G50 to characterize, like even within the flybys, how the signature manifests.
And the mass ratio is like 1,000 off of what we're looking at.
Yeah, no, it's a big mass ratio, but still, these things are, you know, detectable, and it'd be interesting to
Yeah.
hide this in.
Thank you.
Great talk. So have you looked at whether you can see change in chemistry that might help you also identify, like, so look at additional dimensions in your analysis, looking for these bumps and looking particularly at changes in chemistry, because I'm not sure if we're ever going to actually be able to do better in stellar ages. So looking at added additional dimensions might be able to isolate features like this. And have you looked at the chemistry to see if you see chemistry changes?
But that's a great suggestion. And we are planning to actually look at the metallicity versus thickness to see if we can see similar bumps in that.
Right.
So that would be interesting.
In also alpha, yeah.
Yeah,
interesting.
alpha, yeah.
Thank you for the great talk. Did you look in your last slide where you showed the pre-stellar warp and the post-stellar warp, if the rotation speeds of the warp differ, and if they will align up in the future, or if they will get more separated?
Yeah, that is something. That is what we are looking at. We don't have an explanation of why this happens yet, but that is a direction that we are going to look at. Basically, like what we think that is, but we haven't verified this, but what we think that is happening is the difference in rotation speed as a function of C. So basically the thick disk stars have higher scale height compared to the thin disk stars, geometrical thin disk stars. So if the merger were to cause these two populations, this warp, like if the thick disk stars and thin disk stars, they are rotating with different speeds, then that would cause this misalignment. So that is the explanation that we are thinking, but we haven't verified it with the simulation. So that is an ongoing work. I'm still looking into that one.
Great, thank you.
Other questions?
So you did go over this at the start, which data set you'd used, but would you mind just reiterating, so in your observation plot, so where you've got those wiggles, so each point, is that is each point a star? What exactly?
No, we divide the ages into bins, and for each bin we calculate the dispersion in vertical position. That's a proxy for disk thickness, not exactly, that is not exactly the scale height of disk thickness, but that is a proxy that we can use.
Okay, and all from STSS DR12?
No, the region 1 is dominated by the Lamo stars, and region 2 is dominated by STSS-DR12. STSS-DR12 focuses on metal 4 stars. They target some metal 4.
Cool, thanks.
Yeah, just on this plot, I should understand the downturn towards 13 gigayears to be a data artifact, right? Like
I
the fact
think
that
so,
you just don't
yes.
have stars, so dispersion is lower.
Yeah.
Because there's no reason to actually assume, like,
No, I think it should
Yeah.
go up, but I think like this is star force ages, so that's something that we are actually trying to address because there is effect of priors that based on the priors they use, there is a lot of systematic uncertainties, I believe. So that is something we need to address.
Related to kind of the size of these, but with the absolute size that you're measuring here is like a kiloparsec 1.4 or something, whereas some of the simulated ones you were showing went up to like 5 or 6. Is that just kind of selection effect of the observation?
Yeah, like in the simulations we are taking all the stars, so there is definitely, but what we are not interested in the absolute magnitude. We are
Yes.
looking at the relative
Yes,
features, so
sorry.
that doesn't matter. Yeah, we did not.
I was kind of like saying, is the kind of GSE-like merger in a simulation, does it give you this kind of level of height?
Yeah, we are looking at characterizing it based on like maybe like TNG's 50 simulations can tell us more about like can we infer the properties of the satellite or the merger based on the thickness? So that's something we are looking at right now.
Any last questions? If not, let's thank Lekshmi again.
And just while I setting up, our second speaker today is Sebastian Sieber, who did his PhD at the Max Planck Institute for Astronomy in Heidelberg, and is an expert on characterizing atmospheres, particularly rocky planets, using light space-based observatories. Been PI of a couple of JWST proposals, and now he is a Sagan Fellow. He just started in September here at CfA. So please take it away, Sebastian.
Hey everyone. I'm going to talk about rocky exoplanets and characterizing them using and characterizing them from space using different kinds of instruments like Spitzer or Hubble or JWST. And in this case, I'm going to specifically talk about. I'm gonna start over then for the online audience. So I'm Sebastian Sieber. I'm a new Sagan Fellow here. Thanks for the introduction. And I'm characterizing rocky exoplanets from space. I've characterized their atmospheres. I'm still doing that, but now in this talk I want to talk about characterizing their surfaces. And as a little bit of background, you might know that we've already discovered many exoplanets in the past few decades. We now know of around 6,000 exoplanets. And from all these different discoveries, we know that there are many rocky exoplanets out there. And for several of them, we have really nicely measured their masses and radii. So we know their general bulk density really well. And from these measured bulk densities, we know that the majority of rocky exoplanets are most likely to be Earth-like in composition, or like terrestrial in composition, so not like dominated by lots of volatiles. But even though we know something about the general bulk composition of these exoplanets, we still don't know a lot about the composition of the atmospheres or about the surface composition of these exoplanets. And there are different ways to really learn about exoplanets in the end and their emission, the surfaces and atmospheres of these planets. One way is to directly observe them, directly image them. On the right side, you have an animation of the HR8799 system, which hosts 4 really big planets, which are still really young and really hot and emitting lots of emissions, so we can directly observe them. But currently we can only do this direct imaging for big planets, which are far out from the host stars. And we still have to wait for the next generation of space telescopes in order to do the same for rocky exoplanets, which are closer to the host star and also way smaller than these big planets. But for rocky exoplanets, we have other techniques. We can do transmission spectroscopy, where the light of the host star is basically traveling through the atmosphere of the exoplanet, and then different species in the atmosphere will filter out different wavelengths, and we can then figure out which kind of elements there are in the atmosphere of the rocky exoplanet, if it has an atmosphere. But then a really nice technique to not only learn about the atmosphere of exoplanets, but also about the surfaces, is by looking at their emission, using observing these planets basically during secondary eclipses, or by doing something called a phase curve observation. And a phase curve observation is a really nice technique nowadays to really characterize these rocky exoplanets really well. On the left side, you have a cartoon basically showing you on the top what is happening in the system, and the bottom what we observe, so the light curve. On the top, the big yellow dot is basically the star, and then you have the planet orbiting its host star. So when the planet is between us and its host star, you have the transit, so when the light basically dips down the most, so to say. And then when the planet is disappearing behind its host star, you have this smaller dip, which is called the eclipse or secondary eclipse. And during these 2 events, the transit and the eclipse, we see the different phases of the planet, so the different emissions from the different parts of the exoplanet. And during the eclipse, in the end, we study the day side and the emission coming from the day side. And this eclipse depth in the end is telling us something about the emission coming from the day side of the exoplanet, so the reflected light, for example, or the thermal emission. And this depth, for example, if you have an exoplanet with a thick atmosphere, then this thick atmosphere might be good in redistributing heat from the day side over to the night side, making the day side effectively cooler and leading to a shallower eclipse. But also if you have certain species which are absorbing at different wavelengths and you observe at these wavelengths, you would also see that as a shallower eclipse in the end. And this has been done for several hot terrestrial planets already in the past, using Spitzer, for example. And in this plot, I'm showing you some observations of the planet LHS 34b, which I'm going to continue about talking in this talk. The planet is a little bit bigger than the Earth, 1.3 Earth radii, and it has a temperature of around 1,000 Kelvin. And the observations here using the Spitzer Space Telescope were basically that the night side is really cold, basically consistent with 0 Kelvin. The day side is really hot due to this really observed deep eclipse. And this really hot day side and the really cold night side was basically indicative of no heat transport from the day side over to the night side, basically telling you that the planet has no atmosphere and is therefore a bare rock. And the same has been also done for a couple of other different planets like GJ1252b, and also now we do the same with JWST. Just like to repeat, this in the plot are these phase curve observations, with the middle being the eclipse, where the planet is basically disappearing behind its host star. But even though we know from these observations that the planet definitely doesn't have any thick atmosphere, we still learn something about the exoplanet. Because if you don't have an atmosphere, the emission which you have is basically coming from the surface of the exoplanet. And so what you can do now is take this eclipse depth we have measured, which in this case is around 420 ppm, and you can compare it to different kinds of surface compositions. So on the plot on the right side, in the same publication by Laura Radcliffe et al., they compared this one Spitzer data point, which is at 4.5 microns, to a whole range of different surfaces. For example, in blue, basaltic surface, and then in orange, for example, an ultramafic surface. And you can see from this one measurement alone that Spitzer was basically telling us that a basaltic surface is really nicely fitting, but maybe some kind of mixtures are still consistent with the observations. Maybe a mixture out of like basaltic, ultramafic surface or something like that. And the interesting thing here is obviously that these different kinds of surfaces are telling us something about the history of the exoplanet, the geological history of the exoplanet. For example, a granite surface might indicate that the planet has like some plate tectonics leading to crustal reprocessing. And due to the fact that this is kind of interesting, Laura Guiberg wrote a proposal in cycle 1 to basically observe this planet now at the longer wavelengths with JWST. So basically covering the wavelengths between 5 and 12 microns. As you might see, there are like certain kind of features at these longer wavelengths, like certain kind of dips, which might be then like telling you nicely which kind of surfaces it is in the end. And so these are basically the observations we have now. So 3 eclipses, 3 times the planet disappearing behind its host star. The data has been already taken a couple of months ago. And what you see here are 2D light curves, basically. Each single plot is one visit of the system. In x-axis, you have the wavelength. So for each of these panels, on the left side are the bluer wavelengths, on the right side, the redder wavelengths. And then going up in y-axis, you go basically further in time. What you can see maybe here, the color is basically telling you something about the amount of flux observed. What you can see here is that around these times here, it might be a little bit bluer compared to the other times. It's a little bit hard to see, but if you basically adding up the flux across all of the wavelengths, you end up with getting this here, which is the white light curve, so to say, of the planet in these 3 different visits. So you can nicely see the times when the planet was disappearing behind the host star, basically telling you something about the amount of light emitted by the day set of the exoplanet. So you have nicely already the eclipses here in this raw data. And obviously there are like some systematics artifacts in the observations here still. But if we end up reducing this data set, getting rid of the known systematics, and you end up phase folding it and basically binning it, you end up with this nice eclipse observations here with an eclipse depth of more or less 700 ppm, which is detected at high significance. So we can basically do now the same as has been done for the Spitzer observations. The difference here is that the Spitzer observations were photometric, so basically just some flux observed between 4 and 5 microns. But with the JWST observations, we have spectroscopy, so we can just bin the data like we want. So we have the region between 5 and 12 microns, and we can decide on our own binning. And this is what I basically have done here in this plot here. And so you can see again at 4.5 microns the observations by Spitzer, and now between 5 and 12 microns more or less the new JWST observations. The dotted line is a black body model, assuming that the planet is basically as hot as it can be, and then the different colored dashed lines are different kind of surface compositions. For example, the green one is assuming that the surface is completely basaltic, and then, I don't know, for example, the red one is assuming that the surface is completely ultramafic. You can see that there are a couple of surfaces which are consistent with the observations within 2 or 3 sigma, and then there are also 3 of them, like the ultramafic, the feldspathic, and the granitoid, which are ruled out at more than 5 sigma. And so we're still like interpreting these observations and drawing conclusions from that. But in the end, you have to consider that this planet is a planet with open atmosphere. So it is exposed to the stellar wind and to impacts by micro asteroids. And so there is an effect called space weathering, which is basically darkening the surfaces. So all of these different surfaces I'm showing here are assuming that these surfaces are fresh. But if you now consider basically the space weathering effects, which darkens the surface, you can get something like this. So again, the dotted line is the black body. So assuming that the planet is as hot as it can be without any spectral features from the surface. And then the solid green line is assuming that the planet is purely basaltic, which is slightly disfavored at 2.6 sigma from the observations. But if you then basically increase the amount of weathering you have on this exoplanet, so the amount of impacts by microasteroids or the amount of stellar wind impacts you have, then the surface is basically getting darker and darker from that, where you end up basically having in the end a consistency within 2 sigma. You might now say that you can basically take any kind of surface, like a granitoid or whatever, and just increase the weathering so much until it's basically consistent, but that's actually not the case. So we have also looked at, for example, granitoid, which was initially ruled out at 15 sigma from the observations alone. But if you then basically crank up the amount of weathering you have, even if you have like really strong weathering, the observations are still not consistent with the model with lots of weathering. So and this is due to like a feature in the granitoid surface between like 8 to 10 microns, as you can see. So regardless if it's like fresh granitoid or weathered granitoid, we can rule out this scenario. I think I'm also really excited about is that recently we have taken phase-shift observations of the exoplanet with JWST, so that's a program I have led in cycle 2. In the plot on the left side, you can see basically a simulation of what we could expect for this planet. So in blue, these blue diamonds again are the observations we currently have, and then the red squares are what we could expect with our phase-shift observations. And you can see that with our phase-shift observations, we are also really nicely able to constrain certain kinds of surfaces. And the nice thing is also that the near-spec observations, which I've collected, are also overlapping with the Spitzer observations, so we can then in the end independently compare the near-spec observations with the Spitzer observations in the end. So to basically conclude, we have detected the thermal emission coming from this rocky exoplanet at high significance. The JWST observations are just like the Spitzer observations, consistent with really dark surfaces, like for example a basaltic surface. We can rule out several fresh surfaces, but space weathering is improving the agreement for certain kinds of surfaces. For some kinds of surfaces, like the granitoid one, even though you could consider really high amounts of space weathering, we can still rule out these kinds of surface compositions. And in the end, I'm going to reduce and analyze the phase-shift observations of this planet to in the end get a full day-side spectrum of the planet between 3 and 12 microns, and also in the end get the spectrum of the planet and the day-side surface composition of the planet at the different phases of the exoplanet, which I think is really exciting. Thank you.
Thank you very much, Sebastian. Questions?
I assume you've looked at mixes of those, the granitoid and the feldspar and all that. I could imagine, let's pretend we're looking at our moon. And so the side we see has got a lot of, I guess, basaltic surface. And the backside, I assume, is quite different.
Yeah.
And now when you take that, and if it were to go around and get illuminated from different angles, I assume that could mix these things up and maybe explain this better, but I don't know.
Yeah, definitely. So this is obviously like the simplest picture you can take, like just the pure surfaces. In the end, you can have just like mixes like the moon has. So you have like the darker regions on the moon, which are dominated by basalt, and the lighter regions are like feldspar. And so you can just like have some kind of linear combination in the end of these different kinds of surfaces. If like the mixture is like on a smaller level, then it's going to be a little bit more complicated than a linear combination. But yeah, like in the next order, linear combinations are possible, and that's something which we can also look at in the end. Yeah.
I mean, I have a question. Do you have any idea of what's happening at about 11 microns?
Yeah. So I think like people who are doing like theory and geologists are always getting really excited by these outliers. So I think everyone who saw this like around 11 micron got really excited. I, as an observer, I'm always like assuming that's some kind of instrumental effect, kind of. I'm still not completely sure. I mean, the thing which is a little bit weird is that in one of the visits, like this is kind of driven by one of the visits. It's not that strongly seen in the other visits. So it might be in the end an instrumental effect and not actually something coming from the surface. But I'm not completely sure yet.
Oh, interesting. More questions?
This is really cool stuff. So, you know, you were talking about the surface features, but can you also see things like volcanism? Does that change these profiles or other type, like the, you know, not just the rocks, but the rocks in different phases? Right?
Mm-hmm. Yeah. So in the case of volcanism, one really interesting thing, I guess, which will happen is that there would be like gases which would end up in the atmosphere, and there are certain kinds of like gases, like obviously like CO2 or SO2, which would then like create really strong features in the emission spectrum, and we could see that. So if there's actual like volcanism, then we could see that like I think SO2 like around 9 microns, or CO2 then at 15 microns, or at between 4 and 5 microns. So we could see if there would be like volcanism in the end.
And beyond that, can you see differences in the actual molten rock versus solid rock, for instance?
That's a good question. So like in the case of molten rock, typically the surface is basically losing its spectral features. So if the surface would be like covered by lots of still like molten rock, which is not really consistent with like the temperature we're measuring, then the surface would be basically kind of completely featureless. So we wouldn't see any like features in the dayset spectrum.
More questions? I think.
How many rocky planets like this do we know of, exoplanets? And the second part of the question would be, where is this planet in regards to habitable zones and the like? And what is the host star? Is it an M dwarf that's blasted away the atmosphere, or what's going on?
Yeah, good question. So first one, how many do we know of these kinds of planets? So this exoplanet isn't like really special. We just like took this planet because it's really nicely observable. Like it has a bright host star and so on. So the observability is really high. There are also other kinds of planets like this, but the planet is like more observable if it's like hotter, but you don't want to like get basically too hot where the surface is molten, because then you basically end up again with not having any features at all from the different kinds of surfaces. It will be more similar to a black body spectrum in the end. So there are other planets like that, but we basically took like the lowest hanging fruit, the most observable planet. And then regarding the different kinds of parameters for the system. So this is a planet which is really close to its host star. I think I forgot to mention that the orbital period of the planet is just 11 hours. So a year on the planet is really just like 11 hours. So it's really close to its host star, but it's not molten, which is nice. And I think I forgot its host star, but it's either M or a K dwarf. I'm not completely sure, but yeah, it's definitely getting blasted by radiation, I presume.
Okay, was there one more question? Oh, sorry, hand this.
Very naive question. So When we see the phase plot of this exoplanet, we see that kind of asymmetry on this phase plot, especially from the speed side. You can see some bump on the left side, and also when you change to different epoch of this kind of objects, and you see the background baseline. I don't know how to call it. It's also different, and there are some shapes. So how to explain this?
So first part regarding the observations, you mean like these Facebook observations and the asymmetry here. So I haven't done this work. That was my former supervisor. But she told me that she's always getting the question regarding this kind of offset, that it's like, it looks like before the eclipse there's like less flux, and after there's more flux. I think it is just like systematics. It's not like an actual physical thing going on there. I presume in the publication they also checked for like some kind of asymmetry of the phase scope itself, and it wasn't really like justified by the observations really. So the simplest case of like the phase scope being really symmetric around the eclipse was the most preferred model, which they basically found. So I think the lower emission right before the eclipse is only like a systematic effect. Spitzer had different kinds of systematics, like variation in sensitivity across pixels and stuff like that. So there might be still like some kind of red noise in the data itself. I don't remember the second part.
When you observe this object with different time at different epochs, and you see this kind of background changing the shape. Sometimes it's slow, sometimes it's quite flat.
Oh yeah. I think you mean this, right?
Yes.
Yeah. So as far as I know, this is just like sometimes with the mirror detector, it depends on like what the telescope was doing before your observations. So if the planet, if JWST observed maybe like a really bright target, then the systematics at the beginning of the observations might be different. But this is like not really, it's not influencing our interpretation or data reduction at all. And theoretically, you can just like remove the first few integrations, and we still have enough data as you can see.
Any other questions? In which case, let's thank both of our speakers today. Thanks for coming.